All right, last section here, babies, for Chapter 6. What we're going to talk about today is what's called a geometric sequence. So geometric sequence is just going to be an application of our exponential functions. If you remember back, and it's been, as you guys would say, a minute ago, but we have talked about in the past what's called an arithmetic sequence. So again, a sequence is just a set of numbers. And with that set of numbers, you're going to recognize a pattern between them. So for example, in arithmetic sequence, you would see, for example, 2, 4, 6, 8, and then ... represents that this pattern would continue on and on. An arithmetic sequence that we did back with linear functions was where we would see what's called a common difference, where we would add the same number every single time to get every term afterwards. So what we're going to look at today is a geometric sequence, which is going to be very similar, but different, obviously, when we've talked about the differences between an exponential function and a linear function. So a geometric sequence, you're going to see a set of numbers again where the ratio between the two consecutive terms is always going to be the same. Now, ratio is going to be a little bit different word. Instead of using the common difference, we're talking about what's called the common ratio. The common ratio is going to be the multiplier between any two terms. We have seen with exponential functions that you could have exponential growth, where you're multiplying by a common number, or you can see decay, where you're dividing by a common number. So you might see, for example, times 2 every single time, or instead of times 2, you might be dividing by 2, which is technically multiplying by a half, but we're going to be multiplying by a common term or common value every time. That's called the common ratio. So our goal within this section is we're going to try and identify, starting off first with a geometric sequence. Well, first of all, is a sequence geometric or not, or would it be arithmetic, or would it be maybe some pattern we haven't recognized yet? We're going to try and identify what is the common ratio. We're then going to try and use that to try and come up with some guesses, and then we're going to summarize everything and bring it all together and relate it back to exponential functions. So our first example, what we're going to do is looking at this sequence of numbers. I want to know, would this represent a geometric sequence, an arithmetic sequence, or neither? Maybe it's something else we don't know. All right, so the difference real quick between these different types of sequences is an arithmetic. Just know that in arithmetic, we will be seeing addition or subtraction, just like we would see with a linear function. And for a geometric function, we're going to see multiplication or division. So that's going to be the main difference between the two. And we're going to see that if it's arithmetic, we're going to add or subtract the same value. If it's geometric, we're going to multiply or divide the same value. That's called a common difference or common ratio. So example 1, we got 120 down to 60, down to 30, down to 15. So if I'm looking at this, okay, I see down, 120 down to 60. Obviously, we're getting smaller. But when I look at this and I think about, okay, the difference between 120 to 60 would be 60. If I look at the difference from 60 to 30, that'd be 30. Then the difference would be 15. So I see that the difference, subtraction, is not going to be the same. However, if I think of this as divide by 2, divide by 2, divide by 2, notice that I would be dividing by the same number. Another way to think about this, again, just to kind of relate this, is it could be multiplying by a half, multiplying by a half, multiplying by a half. Dividing by 2 or multiplying by a half is going to be the same thing. But the thing here is that because we are multiplying or dividing by a common number, that this is going to be a geometric sequence. Geometric, again, because we're multiplying or dividing. All right, next one, we got 2, 6, 11, and 17. So if I look at, let's say, start off first with the difference between those numbers. 2 to 6, that would be plus 4. 6 to 11, that would be plus 5. 11 to 17 would be plus 6. So notice I'm not adding the same number every time. If I looked at multiplication, I would see times by 3. Okay, and then 6 to 11, well, if I times 6 by 3, that would give me 18. So notice in this one, neither addition nor multiplication would work out. So this one would be neither, would not be arithmetic or geometric. So with a geometric sequence, what we are looking at is for multiplication or possibly division. Multiplication if the numbers are getting bigger, division if we see the numbers getting smaller. All right, so in example 2, what we're going to do is try and figure out what would be the next 3 terms in the sequence. So to do this, what we're going to have to do is find the common ratio. The best way to find the common ratio is to take the first two terms. The common ratio is how you get from one term to the next, called consecutive terms. What I'm going to do is take the first two. So I'm going to take 3 and 6. Now, what I want to do is I want to figure out what I am multiplying by every single time to get my next term. So to figure that out between these first two numbers is I'm going to take the second number, 6, and I'm going to divide it by the first number, 3. 6 divided by 3 would give me 2. Now notice if I think about that number 2, 3 times 2 would give me 6. 6 times 2 would give me 12. 12 times 2 would give me 24. So therefore, I know that my common ratio is going to be that value of 2. So I can use that then to find my next three terms. So I would get 48, 96, and 192. So notice I found that common ratio first by looking at those first two terms and then applied that for my next consecutive terms after 24. So we'll do the same thing here for the second example. I want you to notice one little nugget here is notice how it goes from positive to negative to positive to negative. For an arithmetic sequence, that is something that we wouldn't see. We wouldn't see it flip-flop between positives and negatives. But because geometric sequences are multiplication, if I ever multiply by negative numbers, we do know that if I have, for example, a negative times a positive, that would result in a negative number. If I were to see two negatives times each other, that would give me a positive number. So it is possible for my numbers to alternate in sign if the thing I'm multiplying by is negative, okay? So what I'm going to do is follow that same rule. To find the common ratio, I'm going to take my first two terms, negative 16 and 64, and I'm going to take the second term, negative 16, and divide it by the first term, 64. Now, why I do the second divided by the first always is because I am starting at 64 and I'm going to 16. So I don't want to do this because a lot of you might say, okay, 64 is bigger, so I'm going to divide it by 16. We don't want to do it that way because we start at 64 and we're going to 16, okay? So if I were to do that, that would simplify down to negative 1/4, which means that my common ratio is going to be negative 1/4. Now what that means is that I'm technically multiplying by negative 1/4 every time. Another way to think about this is technically dividing by negative 4, because we can view this as division. All right, so that's my common ratio. So what I want to do then is figure out what would be my next three terms after negative 1 if my common ratio is negative 1/4. So what I would get is negative 1/4, 1 over 16, and negative 1 over 64. Now notice those are fractions. If you have a calculator, it'd be nice to use that because it'll help out. If you get decimal forms, I'm just not going to write the decimals because they're not going to be other than 1/4. Not going to be pretty decimals for us. So, but I want you to recognize the pattern again. We go positive, negative, positive, negative. Oopsies, I actually have these backwards. Sorry, this should be positive, that should be negative, that should be positive. I'm sorry about that, folks. Sometimes I make mistakes too. But notice we have the alternating sign because what we're multiplying by is negative. And then notice that they are getting smaller, so this would represent an exponential decay type problem. All right, now to kind of relate this back, we have been talking about exponential functions, so I just want to relate this back to exponential functions. So let's just say that you have this sequence of terms, 32, 16, 8, 4, and 2. What does this look like on a graph? So understand that in a sequence, okay, this 32 would be my first term, this is my second term, my third term, my fourth term, my fifth term, and so on. Okay, we can recognize that, again, the common ratio between them, if I were to look at 16 and 32, if I would take the second number and divide it by the first, what I'm going to get is 1/2. So I know that my common difference, or common ratio, is going to be 1/2, technically dividing by 2. But graphically, the way we can represent this is that if my first term is 32, think about, okay, my x-axis is my number of terms. So I have my first term is 32, so I'll put a point here at 132. Then continue on, I would have 2, 16, 3, 8, 4, and then 5, 2. You'll notice that as I connect these points, or if I were to connect these points, that what I would get is that curve downward, that exponential decay function. What I'm not going to do, however, is I don't want to actually connect the dots. I almost did it for a second, but just know that with a sequence, we have exactly 32, exactly 16. We don't want to graph in between, so this is technically one of those discrete functions that we talked about before. But I do want you to know that if, and I'll kind of just draw it on here as a dashed line, that if I were to draw that shape, I said a dashed line, it would technically form a curve. So notice how it represents an exponential function. All right, now, again, connecting this back to exponential functions, all right, what we talked about is that for all exponential functions, they're going to be written in the form y equals a times b to the x. So what we're going to do is we're going to apply that equation to our geometric sequence. So instead of y, we're going to call that a to the n. A to the n means the nth term. So yn, well, I can plug in any number there. I could say, what about the 100th term? We can use the number 100 where n goes. All exponential functions, we started with some value, called that a. That was our initial amount. Well, a is going to be represented here by a1. A1, like the delicious steak sauce, would be our first terms where we are starting. Then we always had a multiplier b. So b is our multiplier. Well, in this case, our multiplier is that common ratio called r. And then notice here as an exponent, if I want to find whatever term, that we're going to do n minus 1, okay, n minus 1. The reason why it's minus 1 is because we are starting at some first term, so we're taking away. So if I want to say find the second term, we're already starting with a number, so I'm only going to multiply by that common ratio one time. So the second number, I would multiply one time. Okay, so what we're going to do is we're going to use this equation for a geometric sequence. We're going to try and write an equation and then use this equation to solve. All right, so let's say that I want to find, let's say the 10th term. You know, what I could do is follow the pattern, but what we're going to do is we're going to write the equation for a geometric sequence. So the equation says this, or the geometric sequence can be found by a to the n, which represents the nth term, would be our first term, a to the 1, times our common ratio, and then our ratio is going to be taken to some exponent n minus 1. Okay, so we're going to leave a to the n in here. A to 1 is our first term. Our first term in this sequence is the number 2. Okay, r is our common ratio, so I want to know what am I multiplying by each time to get my next term. So if I look at my first two terms here like we've done before, 12 and 2, if I take 12 and divide it by 2, I'm going to get 6. So that means my common ratio here is 6. So I'm going to write 6 in my equation here where r would go, and then I would keep n minus 1. Now, if you like to keep it consistent with what we did with exponential functions, if you want to put that 6 in parentheses so that it looks like y equals a times b to the x, okay, you certainly can. Now, notice just again the relationship there between an exponential function. My a value here, my initial value is 2. My multiplier is 6. And then we have our exponent n minus 1x. The only difference between this is obviously the n minus 1 is where we see just a little bit of a difference between our exponential function and our equation for a geometric sequence. So now if I want to find, let's say the 10th term, as we're seeing here in our example, the 10th term, what I'm going to do is I'm going to take 10 and I'm going to plug it in where n goes. So using the relationship I got right here, God, we got a lot of colors going on here, folks. If I want to find the 10th term, I'm going to take 2, and I'm going to multiply it by 6, and then 10 minus 1 would be my exponent. Now, just to simplify this would be 2 times 6 to the 9th power. Now, to show you kind of what this means, I would start off with the number 2, and it means I'm going to multiply by 6 9 times. Now, you don't have to do all that work, but that technically is why we have that. So, I just want to explain why, again, we have the n minus, or 10 minus 1, or the n minus 1 in general, is I'm trying to find the 10th term. So notice if I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms there. But notice because I'm starting off at a number, I'm starting off at 2, notice that I'm only multiplying by 6. I'm only multiplying that number 9 times. So that is why we have the n minus 1 in there. But if I were to actually set that into my formula, that value of 10, where I'd get 2 times 6 to the 9th. I'm going to get an extreme number, but I would get, I think I got to move this down a little bit. I don't have enough room. But what I would get is 20, holy strawberries, 20 2,155,392, the year that Columbus sailed the ocean blue. Okay, so that is a huge number because multiplication, again, exponential growth, that multiplication, we're going to see a drastic effect. So we're not just adding here, but multiplying. That number is going to get huge, if you know what I'm saying. Okay? All right, last example here. We're going to apply that same thing we just talked about now to a real-life application. So can we apply that idea of geometric sequences to a real-life example? So it's kind of a good example if you guys have ever used on your computer or whatever, or your Chromebooks, the zoom in or zoom out button, like Control plus or Control minus, or even when your mouse, if you use that little scrolly button, right? You scroll out to zoom out. Okay, every time you scroll one little click, it's going to zoom out a smidge. Okay, so it says here that this, as you zoom out, think of you're looking at a map. I always like to think about Google Maps. One of the things I always like to do is just randomly look at places that I've never been to before, be like, I wonder where that is. And then I zoom out and I'm like, oh, okay, I like that. So as you zoom out, you get to see more of the map. So it says here that as you widen, the thing is going to double in side length. So here it has the number of clicks. So if I were to click once, the side length is going to be 5 miles. Another one, 10. Another one, 20. Okay, so why it says it doubles, knows that the common ratio here, 5 times 2 would give me 10, 10 times 2 would give me 20. So I know that my R value, my common ratio, is going to be 2. So I want to know after how many clicks would the side length of my map be 640 miles. Okay, so that means here I would get 640. So what I'm going to do here is I'm actually going to use my equation for a geometric sequence. All right, so we're going to use that same thing we just talked about, that a to the n equals a to the 1 times r to the n minus 1. That is my equation for any geometric sequence. We already know that my r value is 2. Okay, the only other thing we need is my a value, my a1, my very first value that we know after 1 click we get 5. So I can write an equation that a to the n equals 5 times 2 to the n minus 1. Okay, so that's using my geometric sequence there. Now what I want to know is when I get 640. Now what the tricky part here is that I'm trying to figure out here, n, how many times is it going to take me to get to 640? So I'm going to take 640 and I'm going to plug it right in here where a to the n would go. My nth term is going to be 640. So that's going to equal 5 times 2 to the n minus 1. Now you're going to look at that and be like, oh my Lord, have mercy, how do I solve that? So we just did in section 4, we talked about exponential equations, right? That if I want to solve something that has an exponent, I can solve it using an exponential equation, knowing that the left side and right side of those two equations have to be, or of the equation has to be identical to each other. And it's all about the base. So notice on the right side here, we have a base of 2. That's where I have the exponent n minus 1. The thing I'm trying to solve for is n. All right, now the only issue here is that we do have a 5 in front. We didn't really talk about how to solve something like this, but with this 5 in front, to kind of make it easy to get rid of the 5, instead of multiplying, I can divide both sides by 5. And what that would give me on the left side is 128. So I get 128 equals 2 to the n minus 1. Now using that change of base, right, I can take 128 and can I write it with a base of 2? And you betcha I can. It would be 2 to the 7th power. Don't believe me? Use a calculadora, folks. What that then gives me, I'll write this on the side, is 2 to the 7 equals 2 to the n minus 1. So now using that idea of solving exponential equations, I can take 7 and n minus 1 and set those two things equal to each other, form a linear equation out of that exponential equation, and then just by adding 1, I know that n should equal 8. So I would get the 8th term. All right, now that was a very difficult way to solve that problem, but that was just wanting to apply some of the things we learned. What else could I have done? I could have guessed and check, right? I know that if this is the first term and the second term and the third, I could have just used my pattern and multiplied by 2 until I got to 640 and figured it out that way. Obviously, that's the easiest way to do it, but I wanted to show you guys how we can make use of some of the things we've learned throughout this chapter. All right, so today we focus on this idea of a geometric sequence, which is just an application of our exponential functions we've been talking about up to this point. Again, if you guys got any questions, jot those things down. Good luck on the practice problems. We'll see yous.